Assalamu alaikum. Welcome back for another webinar session on Wim Technologies accuracy for measuring axle load spectra for a pavement analysis and design. This is a purely technical session being conducted by Dr. Syed Waqar Haider. He's associate professor at Michigan State University in the Civil and Environmental Engineering Department. Doc Saab has over 30 years of experience, and he has also been once associated with NESPAC, and he has also served as Director Design for National Highway Authority. He has, mashallah, over 150 technical publications, 45 peer-reviewed journals, 90 peer-reviewed conference proceedings and presentations, over 20 technical reports. He is associate editor of the ASCE Journal of Transportation Engineering. Currently, working as I earlier said, associate professor of department, Michigan State University, and he is also an alumni of UET. Geotechnical engineering, did his specialization in geotechnical engineering from the Asian Institute of Technology and a PhD in his current field. I would like to hand over to Dr. Saab. You guys won't see his video because it's more technical. He wants your focus more on his voice and the presentation. So, Dr. Saab, over to you and Bismillah, please.
Thank you, Hassan. Can you see, everybody can see my screen, right?
Yeah.
Is it there? Okay. Okay, so I just want to talk about the Wim technology. I think I was the first one back in early 90s when we installed the first weigh in motion station on GT Road near Sangjani, near Taxla. So I was at that time, this was 94, 95. So I'm still, so this topic is very close to my heart. So, and I thought that this is also a problem in Pakistan, because I've been seeing a lot of pavements and pavement analysis and design. So measuring an accurate axle load data is really important for pavement design and analysis. So that's why I chose this topic. I'm not saying pavement construction and other part of the pavement are not important, but one of the most significant factor impacting the pavement performance is the axle loading. And as you all probably know, most of you in civil engineering, we still use in the US AASHTO 93 design. We use easels. But now we are in the US, we are transitioning to the mechanistic empirical design. This is a new AASHTO called Pavement ME, and in which we don't use easels, so we use low axle load spectra. So importance of Wim technology is even more now, that we need to have more accurate axle load spectra for our pavement design. Okay, so I'm going to talk about some background why we need Wim technology to measure axle loads on highways. What type of Wim errors are associated with the Wim measurements, and what are different Wim systems, and how we measure their performance. So this is a lot of research we have been doing in the US on these Wim technologies. I'm part of a couple of national studies on the Wim in the US. And I will also talk about some factors. So we cannot put a Wim sensor on any site. There are certain factors we need to consider while we select a site for a Wim sensor installation. And we looked at all different states in the US, and we have a long-term pavement performance data, which contains all the Wim data for different states. And I'm going to talk about some accuracies we can achieve by different Wim sensors. This is important because they are actually using these sensors, and these accuracies are coming from the field data. I'm going to talk about the cost of different Wim sensors over the life cycle cost, or what is the expected life of each of those sensors. And I will also look at the calibration needs for Wim, because Wim measurements, they will contain different types of error. Basically, these are systematic and random errors. So how we can eliminate systematic errors uh, by using the calibration of these sensors. Okay, so axle load spectra, I'm going to talk about what is the impact of Wim error on pavement performance. So if you have low data with high error in it, so it is going to impact your performance. You will be over and under designing. So I'm going to talk about that. And in the end, I will summarize that. So, okay, so why we need Wim? In the US and in the Canada or in Europe, mostly we use Wim sensor in the roads to measure the vehicle and axle loads. And these loads are used for pavement and bridge design.
डॉक्टर
Yeah,
साहब सॉरी टू कट यू अगर आप ये अपनी स्क्रीन दोबारा शेयर कर लें वो बेहतर है हम ये
yeah. There is something in there. I can
there's
see.
some issue
Just
going on. Thank
let
you.
me. Yeah, no problem. You can see it now?
Yeah.
Okay. Yeah, somebody's writing on the screen. I don't know from where it is coming. So.
Please don't write on the screen. All right, done.
Okay. So typically this data is used for pavement and bridge design. We also use this axle load data for weight enforcement. And you must have seen some base station on Motorway. And actually, I was part of it back in the early 90s. We installed several way stations on Motorway. And I'm going to tell you what is the difference between the Wim sensor I'm talking about and what they use in those way stations. Now, these data are also important for freight travel demand modeling. So, in the US, they use the Wim data to actually estimate how much freight is being moved at the network level. Now, Wim technology is available since early 90s, and we were, I think, in early 90s, in 94, 95, we installed that in Pakistan, okay? So, but in the US, most of the states now are using this Wim sensors. Now, the sensor accuracy is improved over time. So since the technology is improving and the sensor cost and the accuracy has improved over time, but still we have different technologies available to the user so that you can have different accuracies along with the associated cost. There are some challenges which are related to data accuracy and consistency. And I'm going to talk about some of those issues for these sensors. Okay, so as you know, we have sensors on the road as the truck is passing through this. So that's why it's called weigh in motion, because we are weighing a truck. When I say truck, it has different axles. You may have tandem, single, tandem, tridem, and quad axles. So we are going to measure the weight while the truck is moving. Now, actually, we take the truth as a static load of the axle, which is at a very high accuracy. The static scales are much more accurate, but the moving load has some dynamic force depending on the pavement roughness. So it will induce some error into your measurements. But the reference for the load is a static load. So that is measured on a static scale with the accuracy of even less than 1%. Now, what are different technologies being used all over the world? Right now, we have bending plates. So most of the sensor I installed in Pakistan were bending plate type. Now, also, there are sensors available that are called load cells. These are more like plate type sensors. So the bending, or they use a technology in them like strain gauges. So there is a change in strain, and that is related to the weight, which is causing that strain. And there are also strip type or linear sensors. One of them is a quad piezo and piezo cables. So they can be installed very quickly in the pavement. But the one caveat for these strip type sensor is their life is not that long. So every 2 years or 3 years, you have to replace them. So I'm going to talk about the cost of these different technologies. But before I do that, I'm going to talk about some of these what do we mean by the accuracy? So when we talk about the Wim measurement accuracy, we talk about systematic error and random error. Systematic error, if you see this, target picture. So let's say our target is in the middle. So if you are hitting the target, you are really accurate and there is no systematic error. But if you are systematically hitting on the side, that means there is some systematic, your data is accurate, but it has some systematic error. And in our term, in statistics, we call this a bias, so because you are away from the target for a constant value, right? So this is called bias. And if you are hitting the target, but you have a high variability, so if you take an average of these red dots, we may get close to the target, but there is a high variability. So this is you can think of this as a random error. So this random error is part of the technology and other factors I'm going to talk about. But systematic error we can remove through calibrating these Wim sensors. So that's why the calibration is really important for these vein motion sensors. Now, another way of looking at the accuracy is if you have a systematic error, you will have two distributions where the means are different. So if your spread is the same, so you have the same standard deviation but different means. But if you have accurate data but with more random error or variability, so you are looking at two distribution which may have same mean, but they may have different standard deviations. So this is how we actually quantify the error in the vein motion. Now, how we measure error, it's a relative error between the static weight. So when we do calibration, we actually measure the single tandem and the gross vehicle weight, or if you have a tridem, you can measure that on a static, because static has a very good accuracy of less than 1%. So that is our truth, and we want our Wim weight to be close to that static. If those two weights are close, we have minimized the error, right? So that's what we want to achieve in calibration. We want to have a relative error which is really small, and I will show you what are the limits we use in the US for these type of error. So if I take this error as a random variable, so it will become a normal distribution. That's what typically we see. And if you have zero bias, or your systematic error is not there, so in that case you will have a zero mean and you will have some standard deviation which is part of the random error. Now there are two different standards used in the world to actually specify the accuracy of these Wim sensors for the axle load measurements. One is called the ASTM E131809. This is the ASTM standard used in the US. And then we also have European road specification, which is called 323, which is used in the Europe. Most of the stuff is similar, but European specifications are more elaborated, and I will show you what are the main differences. But the accuracy requirements are almost similar for the pavement design and bridge design and data collection. Now, here is the type 1. This is from ASTM. The type 1, this is the category for pavement design. That's what we need to achieve. These accuracies we want to achieve for pavement design. So wheel load should have an error of less than plus minus 25%. If you go to gross vehicle weight, so if your accuracy is less than 10%, plus minus 10%, so data is still acceptable for pavement design. But if you have higher errors, then the data will not be very useful for the pavement or bridge design. So these are the accuracy requirements by ASTM, and all the Wim in the US, they have to meet these specifications. Now there are other types for other, for freight and for other type of needs. So the accuracies are different for those, and accuracy is more stringent for enforcement purposes. Now I'm talking about for the data collection for pavement design. So just keep that in mind, and I'll talk about that later too. Now, what factors can impact the Wim system performance? That will depend on the site and the climate. So this is the map of the whole US, and we have looked at all 50 states in the mainland US. And this is the data. These are different types of sensor being used in different states. And this is coming from long-term pavement performance data for pavements. And you can see most of the sensors are either bending plate, piezo cables. We have quad piezos, but most of the sensors are bending plates and piezo cables in different states. So why they are using different sensors, and that will depend on the cost and how many sites they have in each state. So this is based on the average number of sites. If they have majority of bending plates, so we designated that state as more dominant bending plate state, right? So that will depend on the cost and how often you need to replace. And I will show you the accuracy data from these sites. So this is the data available to us. So we have all the data of accuracies after the calibration for these sites. Now we had, before we looked at the data, so we want to actually have some quality, some restriction on the quality. So we have high quality, which meets, the ASTM standard, and we put some limits on the bias. For the low quality, the bias will be slightly higher, because this data is coming from states, and sometimes there is error in the data, so we want to eliminate those outliers. So that's why we are using these different limits for the bias for gross vehicle weight. Now to measure the accuracy in the field, we analyzed about 170 sites distributed all over the US, and they are almost more than 400 records for the calibration. And we looked at those, and I just want to quickly highlight these data qualities. LTPP RQD is a research quality data where they have used very stringent requirements for calibrations. So this is part of the experiment in LTPP. There are about 36 sites. They are monitoring it very closely. So we anticipate this data will be quite accurate. But other data, they are coming from the state. So they are not applying the same standards of calibration as the RQD sites in LTPP. So based on this, so here is the distribution of the gross vehicle weight bias. So you see most of the bias is hovering around 0. So if you do a proper calibration, your bias has to be close to 0, because we can eliminate the systematic error. But still we see in some sites there is some bias. And this is because of the sensor. But most of the values are close to 0 for bending plate. For load cell, we had limited data, so that's why we're not seeing a lot of frequency of the sites. But for quad piezo, again, it is, more probably close to 0, the bias. But for piezo cable technology, you will see there is a much higher bias even after calibration. And same is true for the standard deviation of those during the calibration and the total error. So you see much higher total error in piezo cables, whereas bending plate and quad piezo and load cell are giving you, quite accurate data. So just these are coming from the actual site. So I just wanted to show you, once we analyze the data, what is the range of these error in actual field conditions. Now here is the summary of those accuracies. If you see, this is the first one is the bias. So you see, even after calibration, we have some bias left in the bending plate, which is almost close to 0. Quad piezo, we have some bias, and piezo cable has the highest bias. And we see there is a total error is less than 10%, except the piezo cable. So you can expect there will be higher error in the piezo cables. Okay. So these are the accuracies coming from the data, and these are achievable accuracies in the field. So that's why this is important, because this is coming from all over the US. Okay. So, and these accuracies can be achieved in the field. Okay, now there are several factors which can impact the accuracy of these sensors. Climate is one of them, because in US, where I am, it is right now it's below 0 right now, and it can go up till minus. I have seen minus around minus 50 degrees. So it is winter is really severe, and in the north part of the US, but south is it can get hot. So these temperature variations can impact some of these sensors, and I will tell you when I talk about that. Pavement type, if you can install these sensor over rigid or flexible, that has some impact. road geometry, which is the grade, longitudinal grade of the road. That can also impact the deacceleration or acceleration of trucks, and that can impact the accuracy because we are measuring the load dynamically. Now, sensor type is the main one of the main factor. It is going to impact the the sensor accuracy for sure. You know, each sensor type has a different technology, and this is a main factor. Sensor type will impact the accuracy of your load. Sensor array is we can do multiple sensor in one lane or in the different wheel paths. So this is important. So if you have more sensor arrays, actually your system will be more accurate. Okay, so okay, why it's going back? Give me 1 second. Okay, and the speed points is when you calibrate the sensor, how many speed points you can calibrate at different speeds, because in the actual field, trucks may have a range of speed. So we need to calibrate for a range of speed for that. Okay, now what we want to do is we wanted to quantify from the data that how we can select a site so that we can improve the accuracy. So these are just, these can serve as a guideline for agencies to select the WIM equipment based on the site and the sensor related factors. So we developed some decision trees based on the data. So that will show us that if I want to install a different type of sensor, what should be site characteristics? So in this case, you see sensor array, sensor type, speed points, you know, climate, dry or wet, and pavement type, they are important factors. These are actually with the importance, 100% mean it's the most significant. And then these are the 5 really factors which are impacting your accuracy of these sensors. Now, I just want to go over, you know, this is a decision tree based on the data. So if you want high accurate data, you should either go to a bending plate or quad piezo. So, and then if you need more accurate data, you need to have a staggered sensor array. So in this case, your bias will be even less. But if you go to other sensor arrays, you can have slightly higher bias. And then you need to, if you are in dry or wet region, you can, in wet region, we have seen the accuracy is better. Then on AC pavement, the bias will be more. And if it is on PCC pavement, the bias will be less. So based on this, we can select what type of pavement and where we can install a particular type of sensor. And this is for piezo cable. So we have different factors. Based on the accuracy, we can pick those factors based on the decision tree. Now, this is based on the total error. The first decision tree was based on the bias in the data, and this is more on the total error which we get from these sensors. But it has similar results, so we can pick up a site based on the accuracy requirement. Now, decision tree models are really simple to use, but they are entirely dependent on data. So in the data, we had mostly the error, which is less than ASTM requirement of 10%. So we don't see a lot of variation. So this decision tree is based on this data, which is already accurate. So we don't have data which is totally, showing us a lot of variability. Now, so I want to talk about some how this is going to impact actually the systematic error. Now, if I want to see if certain sensor is giving us accurate data, I can analyze axle load spectra before and after calibration. And if I see a shift in the axle load spectra, then I can develop a model. Just by monitoring the axle load spectra, I should be able to identify whether there is a need for calibration or not. So that's what we are doing here. So we want to develop some model to see calibration drift based on the load spectra. That means you don't have to do the calibration. If you have the load spectra data, we can look at the shift of the load spectra, and that can tell us that your sensor needs calibration. So we have data before and after calibration accuracies, and also we have load spectra before and after calibration. And based on that data, we have developed these some models which are simple to use, and that can tell you that your sensor need calibration or not, right? So this is what I want to highlight. So these are the sites we use where we have actual data for before and after the calibration. When I say data, it is accuracy data and sensor accuracy and also load spectra. Now, most of you will know who deal with the pavements. When we look at the gross vehicle weight or the axle load, I hope everybody understands what is an axle load spectra. It is simply a distribution of load, and this is the frequency. So if you look at the tandem axles, typically this shape, this is called a bimodal shape. So typically you will get two peaks. One is because of the empty vehicles and the other one is because of the loaded vehicles. So we typically get two peaks and we call it bimodal. And I have done a lot of research on this topic. We can model these using a mixture of two normal distributions, or even if a log normal or normal distribution, or gamma distributions. We can model this in terms of a distribution. We can combine two distributions. Now, what we are trying to do here is we have 30 days of data before calibration and 30 days of data after calibration. So we can get a load spectra and we can compare that with the accuracies if there is a change. So we looked at different shape factors for load spectra. So one of them is actually mean of being greater than 26,000. So if your data is more than 26,000, we are looking at those. Basically, the higher load will cause more damage. So we want to identify those, and we looked at the mean, shift in the mean, standard deviation, all of those shape factors based on the single and tandem load spectras. And we want to relate it to the difference in the bias for tandem. And we got this model, which is quite accurate for these data. So this is telling me if I see a shift in the load spectra for more than 26,000 pounds, which is around 1,500 pounds, so I expect there will be a bias of about 5%. So just by looking at the shift of the load spectra, we can see there could be a negative or positive bias. If our shift is on the left side, so in that case, we will have a negative 1,500. So in that case, our bias will be -5. So that is telling me our sensor will need calibration, because calibration can only remove the systematic error in your measurement. So similarly, we did a model for a single axle. In this case, if your single axle mean is the mean of the distribution is shifting by more than 500 pounds, let's say we do we get a load spectra in 1 year and we compare it with the second year. If the mean is shifting by more than 500 pounds, we expect there will be a bias and your sensor needs calibration. So these such type of tools are important from the practical point of view, because people can look at the load spectra and they can identify if there is a need for calibration of these sensors. Okay, and similarly, since tandem axle is highly correlated with the gross vehicle weight, so if you see the correlation on this side, and then we develop the same, for the bias based on the gross vehicle weight is highly correlated also with the mean difference of axle more than 26,000. And this is the simple model to actually, if you have a gross vehicle weight, the tandem axle data, we can still also estimate the bias based on the gross vehicle weight. Now, this is useful. Like I said, it will be useful for identifying if there is a need of calibration for certain site just by looking at the load spectrum. Okay, so I want to just show some more practical data. So we talked about piezo cables, which is a piezo sensor, quad piezo, bending plate, and load cells. This is the expected life of these sensors from historical data in the US. So piezo cable will last about 2.5 years. Quad piezo has an expected life of 4 years. Bending plate has an expected life of 7 years. And then load cell has an expected life of 11 years. Also, we have the typical ranges of the cost for these installations and some of the maintenance involved over time for these type of sensors. And you can see piezo cable is the cheapest. These are in dollars, US dollars. And I calculated the average value, and the most expensive is the load cell. But at the same time, you are spending $48,000, but it can give you a life of 11 years. So you can still use this sensor for 11 years. That means if we do a life cycle cost analysis based on this data, so that means if I'm getting a present worth for 10 years, so that means for PC I need to replace maybe 4 times to meet a 10-year period, analysis period. QP I have to do probably twice, to come up with the 10-year period, and maybe bending plate twice, and load cell just once. So this is telling me still piezo cable is the cheapest if you compare over life. But if you look at quad piezo and bending plate, the bending plate is the next cheapest here over the life cycle cost, and this is also equivalent unit annual cost. These are the two criteria we use to compare different alternate for life cycle cost. So, but at the same time, if you are going for a cheaper alternate, but then you have to make sure you do a proper calibration of these sensors to obtain an accurate data. So there will be more demand for more accurate data. And for that, we need to actually be very vigilant for calibration of these sensors. But bending plate to me is really accurate. And most of the states, for example, California is only using bending plate because they want more accurate data, but the cost of that will be higher than the other sensors. So you can pick up the technology based on the resources available, but at the same time, you need to also worry about what accuracy of the data you can get. Now, based on this, I want to just show you if you have more error in your data, how it is going to impact the pavement performance. Okay, when I say performance, it's the cracking, rutting, faulting, and IRI for rigid and flexible pavement. So I'm going to just show you some results. Okay, I talked about different factors. So all these factors will impact the error for sure. Okay, so now this is the equation I showed you before to calculate the relative error. Now I can introduce an artificial error into this, and I can use Monte Carlo simulation to generate some load spectra with this error. So I used, plus minus 10% bias. So if you see that, this is actually this is the random error. If you have the mean is same, but you have different random errors. And this is the bias. If your bias is changing, your distribution is going to shift either to left or right. Excuse me. So I use the actual load spectra from the LTPP data. So this is coming from 3 sites in LTPP from different states. And I use the Monte Carlo simulation in this case. I can generate from the cumulative distribution, I can generate random numbers, and I can get a load spectra with a certain amount of error. So these are the load spectra for these assumed, right? What is the random or the systematic error? I can use these load spectra in the pavement ME to predict alligator cracking, longitudinal cracking, rutting, and ride quality, transverse cracking for rigid pavement, faulting, and IRI for rigid pavement. Now, I'm going to explain that here. So if you have more systematic error, so this is for flexible pavements. What we anticipate from the prediction is if there is a 10% bias in your data plus bias, you will have 25% overestimation in the life, which translates to about 5 years for flexible pavement. And if you have a negative 10% bias, that will translate to about 7 to 9 years of underestimation in the life based on fatigue cracking. Similarly, if you have this is for rutting, so you will estimate if there is a 10% bias in your data, 30% overestimation in life, which translates to about 4 years, depending on, if it is a thick or thin pavement. And if there is a negative bias, there will be 45% underestimation. So what this is telling us is negative bias you will underestimate and you will be under design your pavement. So negative bias is really bad in the Wim data. And this is for IRI, for roughness. Again, there is a 10% change, we'll have about 10% overestimation, which translates to 1 to 2 years. And for rigid pavements, if you see a 10% change in bias in your data, will translate to 5% overestimation in life, which is about 1 year, but negative 10% will cause about 10 to 70% underestimation, which will translate into 10 to 14%, 14 years of life. Okay, so this is a significant impact of the error in your load spectra. Okay, so this is for cracking, and then this is for roughness. Again, negative bias will cause 30 to 40% underestimation in your life. So, so that is telling us if you have uh, uh, error in your load spectras, that is going to impact your design, and that is also going to impact your performance of the pavement in the real field. Now, okay, I have already mentioned these things. So this is a summary of it. So we expect about, if there is a negative bias, we expect about change in life from 15 to I would say about 7 years, depending on the thickness of HMA. This is for PCC, and this is for HMA. So, and that shows for thinner pavement there is a more change. There is a more effect of that load as compared to thicker pavements. So the impact of measurement error is more critical in rigid pavement, especially in pavement with thinner slabs. So it is going. All these distresses I'm talking about is load. They are all load related. Thermal cracking is not a load related. It is independent of the load because it's happening because of the temperature changes. So these are all distresses which are dependent on the load. So that is why they are being impacted by your load spectrum. Okay, so in the end, I will say there are 4 types of sensor technology right now mostly available in the US. So bending plate and load cells are more accurate sensors. We see very consistent accuracy of these, and they will give you a longer life, but they will cost you more. So in order to match your resources, the next option should be quad piezo. And piezo cable, we have seen a lot of effect of temperature. Michigan used to have a lot of piezo cables, and they replaced all with the quad piezo. Because of the temperature variation can cause variation in the load measurements. Now, sensor array is important. How you arrange different sensor on different lanes. We have parallel sensors or we have staggered sensors that will impact the accuracy of the whole WIM system. That's what we see in the data. Speed points are important. You need to calibrate using multiple speed points so that you can actually reflect the truck speeds on the roads. Now, like I said, bending plate and load cells are not dependent on the climate, so temperature variations or dry or wet. On the other hand, quad piezo, especially piezo cable, we see there is a significant impact of the climate on these sensors. So your load will be more variable in let's say in winter versus summer. So there is some effect of climate on these strip types or linear sensors. Now, in summary, I will say reliable and accurate Excel load data are essential for pavement design and analysis. So we are designing pavement for these loads. Now, most of you are designing there using ASTO. So you are going to estimate the design easel for, let's say, 10 or 20 years. So if your estimation of easels is not correct, that means you are over or under designing your pavement. By the way, we can calculate easels or track factors from the Excel load spectra. That's how they are collecting. And I'm not sure, I'm going to talk about this. I'm not sure in Pakistan we have enough reasonable data to come up with our own loadings. I have seen people are using the force power law to get the load equivalencies. And I have seen easel values of 100 million, 150 million. You cannot apply ASTO design method for those magnitude of easels. In the US, typically interstate will have about 10 to 20 million, and that is still a large extrapolation or extraction of ASTO. So that's why we are moving towards now mechanistic empirical design, because ASTO has its own limitations because it's an empirical method. Now, the results also show the cracking performance of both flexible pavement because cracking is very significantly impacted by the load. I'm talking about the fatigue cracking. So the negative bias in your measurements will impact your fatigue cracking, and you can over or under design your pavement based on your axle load data. Now, the pavement designed by using axle load spectra with the negative bias will have the most critical impact because you will be actually, it will not be conservative. You will be under designing your pavement. So that's why it's very critical. If you have a negative bias, you will be actually getting a higher load than actual because of this error, and you will be under designing your pavement. Now, while we all understand in ASTO also we use a reliability because that reliability can account for some unforeseen variance or variability due to construction and the traffic estimates. But I have several papers on this. Even the reliability will not account for that high error in the Wim. So if you have Wim error, even though we apply a reliability, you will still under design your pavement. So what I recommend, we should use less than 5% threshold for a negative bias. As long as it is less than negative 5%, I think we have a reasonable data for pavement design. Now, Wim scale should be calibrated periodically, what we have seen for different sensors. If you have a piezo cable or quad piezo, for piezo cable, you have to probably calibrate every 6 months because those sensors are accurate when you calibrate, but over time there is a drift. And you will have a lot of bias in your sensor. For quad piezo, 1 year frequency is okay. For bending plate and load cell, 1 to 2 year frequency for calibration is fine. But the method I explained here, if you have load spectra, we can see how those load spectra are shifting over time. And that will identify also that we need a calibration for the sensor. Now, the allowable Wim accuracy can be determined by considering the axle load spectra. That's what I mentioned. And we developed some simple models for use. And I think this will be, we are still working on this study. And we will be developing some tools which a lot of people in the US will use for these Wim sensors. Okay, so that's what I had. So now I can answer questions. So go ahead, Hassan, if there are any questions I can answer. Hello, Hassan, can you hear me?
Yes, sir.
Yeah, are there any questions?
We're waiting. Ladies and gentlemen, please, if you guys have any questions, post them on the chat. All right, we have a question. Which type of sensors do you recommend to be installed on motorways here in Pakistan?
Okay, I think what they have, when I was there back in 90s, it was mostly bending plate, which is quite accurate sensor. But I don't know what they are installing now. But if you are doing, okay, now that's a good question, and I think I need to emphasize that. We need more accurate sensors if you want to actually force axle loads. So in that case, even the slow speed or static sense, those scales are better because you want to enforce the axle load, right? But for pavement design, we need to embed these sensors in the mainline pavement. These are not, so in the US, you have, so you see those weigh stations on motorway, right? So that means you need to divert a truck toward that weigh station so that they can measure the weight and they can see if it is overloaded or not. In the US, they have weigh station for enforcement, and then they install these sensors in the main line pavement, okay, in all the lanes, so that every truck is being weighed. And they don't use that for enforcement, they are used for data collection. So what I see in Pakistan, we don't have any sensors which will actually show you the actual amount of loading which is going over that road, especially on the GT road. I was there for like almost 8-9 years, and that GT road, part of the GT road is always under construction. So a lot of overloading on the GT road. I think in that case, we need to have maybe quad piezo can be good for data collection, because since we don't have the actual load equivalencies or truck factors. I still remember there is a 1995 NTRC study most of the people are using, and that is based on the very small sample. So it is dangerous to actually use it still, because the loading might have changed in it's almost now 30 years. So they need to install sensor on the main line for data collection, and then they need to have a more accurate, because they're enforcing in those way stations. I think bending plate, they were using bending plate at one point. So that if the only caveat there is the cost of bending plate sensor is quite high. But if you can maintain, quad piezo, which is cheaper, and the technology is changing day by day, so it will be much more cheaper in the future. So quad piezo is fine for data collection. Go ahead.
Another question is, are such measurements in operation in the other states in the United States, US states?
Yes. So you're talking about the measurement? Yes. We have about 60 WIM sites in state of Michigan. This is just one state. So every state is monitoring their weight, and then they have weigh station like we have on the motorway. So that is for enforcement. So police will operate those, and then they will randomly measure the weights because they can see the data from their main line. So if they see there is more overloading, then they will go to weigh station and divert the truck, and for enforcement, they will measure it more accurately.
There's another question. Please recommend another pavement design method which caters ESALs more than 50 million, as you said it correctly. That in Pakistan there are more ESALs to be dealt with.
I've been using that too when I was there, right? So the problem is no method will give you, it will all depend on the material and construction. So whatever design values we use, no method will give you a rational pavement design for those loadings, okay? So, but if you use more mechanistic, it will be much more rational, because you are relying on the pavement response to the load, rather than using an empirical method, which was, I don't know whether people know, maximum easel on ASHTO road test, where the ASHTO method was designed, was about 2 million easels. And we are trying to extrapolate it to 20, 30 to 100 million. So that is a too huge extrapolation. So if for Pakistan conditions, I think it will be better to collect more data so that we have more accurate data and we have some idea of the load spectra. I never saw Excel load spectra there, but that can capture, and then we can use more mechanistic design analysis and design methods. That will be more rational for Pakistan. But having said that, the material properties we use for pavement design and the construction quality we have. I was there when I was on motorway when it was being constructed. So you can see the quality of construction for motorway. I'm talking about Lahore Islamabad M2. It has, it was, although it was under designed, because we only had, I remember, 13 centimeters or about 5 inches of HMA. But one thing was there was less overloading, and the quality of construction was really good. So that pavement survived for almost 20 years now, right? It's more than 20 years. Although we did the overlay, I think 6-7 years ago, but that pavement that is the only pavement I remember which gave you the expected life. Although it was under design, but because of good construction and control of, to some extent, the overloading, it gave you enough life of that pavement. Go ahead.
What is the duration for which data should be collected? Time duration.
Okay, so in the US, all these WIM are 24/7 months. They are collecting every day, every hour. Okay, so that's why I'm saying this is for data collection. So they have huge data, and I have analyzed several times, about 5 years of data every day. So they generate all the data every day for every month for all years. So for more data you have, more is our confidence on our loading, right? So in Pakistan, typically people use samples, and sample may not capture all the time the population of the overall, overloading problem in Pakistan. Go ahead.
There's another question that somebody who has worked on Chashma DI Khan Road for a sugar mill project, connecting a sugar mill to a road, they say that it is observed that sugarcane trolleys are overloaded. And is there any specific criteria for pavement design for such roads which connect the sugar mills and heavy
You
loaded?
know, uh, yeah. So this is a challenge. This is a seasonal challenge. You will not have those trolleys, and I think it will be probably this time, right, in November, December, when you have sugarcane. So you need to measure the weight of those, and then you can calculate some load equivalencies based on that's what you're using there, right? But if I have that, I'm going to actually model that pavement mechanistically and look at the pavement response, what strain level it gives you. But this is not, I don't think so sugarcane is a problem throughout the year. It is seasonal issue.
What the load control? Any difference between the Wim data and the load control regime? Because some people are saying that Pakistan they morely prefer the load control regime rather than working on the data Wim data or any of the.
That is the problem there. Last time I was there, I have talked to the people in NHA and all, people who look at the national network. The problem they think is enforcement will eliminate, but what we are designing is not according to the load. For that, we need to have the real data, which is actually going on those roads. Right now, we are trying to estimate those, and we don't have an idea. But enforcement alone, if you design your pavement for those loads, sure, then it will probably perform better. But at the same time, it may cost you more. But enforcement is a tool they use still in these developed countries, because still overloading is prevalent in on highways in the US also. So you have to enforce overloading, but at the same time you need to have a good data for pavement design. So both of these things can help you extend the life of your pavement.
So connecting with this question that if wing stations are affected in controlling loading, what is the role of sensors in checking overloading on roads? Plus, keeping in view that sensors are expensive to install, why not use correlation graphs instead?
Okay, so see, enforcement, you cannot measure all the vehicles for enforce. I did it myself on motorway back in 90s. So you can only measure some, and that is a sample of data, but if you have sensor in mainline pavement, you are measuring every load. Load spectra means it is the distribution of the load from very low to high when empty or loaded. So you have the whole distribution. That's what you need for pavement design. So what was the other question on that? There was another part of
Keeping in
I
view
forgot.
that sensors are expensive to install, why not use correlation graphs?
Correlation between what?
Correlation graphs instead, they say. Okay.
No, correlation between what? So these correlations are dependent on data. So if you have more data, your correlation, your confidence of your data will be much higher, right? So you develop correlation based on sample data. So what confidence you will have on those correlations?
Okay.
So first,
Well,
first
sorry.
you need to collect the correct data, correct amount of data, so that you actually capture what is the range of your problem, right? Go ahead.
Yeah. What is the procedure or time period of calibration and maintenance of sensors?
Oh, that's a good question. Okay, so typically, I can give you an example in Michigan. They do calibration every year. So you need a truck, or which is the most common truck on your highways. We use class 9 here. We have two tandem axle behind in the trailer and one front axle. They will measure that. They should know the actual weight of the axles uh, with a very high accuracy, because that is your truth. And then they will run that truck on sensor at multiple speeds, and that might take. They will do it in the day and in the evening. It may take a day to calibrate one lane of sensors. Okay, and then they compare what is measured and what they actually know the true weight of those axles and the gross vehicle weight. So based on that, they will calibrate the gain factors inside the Vim so that they can eliminate the bias. But sometimes, if somebody is experienced, the technician, they can do it in a couple of hours. Our sensor can be calibrated. But you need a truck to calibrate the actual truck, which is actually using these roads. Go ahead.
What is LTTP traffic data and NALS shape factor and its abbreviation?
Okay, LTPP is the long-term pavement performance data. We have been observing pavement back from 91. So in different states, they have designated certain sections of pavement. They have instrumented them. They have Vim sites on them. They took material samples, and they are monitoring the performance of those sections with the anticipation that this data over longer period, it's almost more than 20 years now. So we can look at the performance and what type of pavement material were used, what construction, what loading is there. So we can calibrate these performance models for pavement ME. So it is a long-term pavement performance data where they are collecting all this data in a database, which is available publicly in the US. And we can look at all these sections and we can calibrate the performance, all the performance models from the real pavement. And these are the sections distributed in all states in the US. So it's a huge undertaking. They are taking it since 1987, I think they started this. Oh, NALS is a normalized axle load spectra. So you basically you have the frequency, the number of, let's say you have different bands in load spectra. Let's say for tandem axle, it's 2 to 4,000, 4 to 6,000. And then you have frequency. How many of the tandem axles are within those? You can divide this by the total to normalize it to 100%, right? So that is called normalized axle load spectra.
So what is the additional approximate cost impact of using sensors as percentage of total cost of roadway?
It is nothing. Okay, so if your motorway is costing you 100 billion rupees, right, at that time, so imagine the cost of that sensor will be maybe like 100. If you do 1 or 2 or 3 installation, it will be couple of thousands of dollars, right? Couple of $100,000. But if your payment can survive another 5 years because of more accurate data, the cost of sensor is nothing as compared to the cost of the payment. So that's why in US, every state has several of those sensors in the mainline pavements.
Sample data, okay, sorry. Where do we have Vim technology installed for axle load measurement in Pakistan? Do you have any example of?
I think when they are measuring on the toll plazas where they have they measure the weight. So they have weigh in motion. They are called slow speed weigh in motion because they can go up to 20 kilometers per hour. Because lower the speed, they say the accuracy is little better than the high speed. What I talked about is a Vim is a high speed at the posted speed limit, right? In the US, it's mostly 70 miles per hour. But you can measure at the slow speed. I think all the Vim sensors in on motorway, they can measure the axle load and the gross vehicle weight. And I'm not sure they have that on Indus Highway. They were planning. I'm not sure they have those on Indus Highway also. But now, before I mentioned that, because I did a lot of work when I was there on this, how you select a site. So we put one close to Sanjani because we thought there is a lot of overloading coming from the Marga quarry, right? So you want to capture the load at the source. So so you need to pick up some strategic locations for these load specters so that you can capture those overloaded vehicles. And on the motorway, I know close to Salem Chowk, there was aggregate coming from Sargodha quarries. So they were carrying a lot of, those heavy loaded trucks. So you want to make sure you install these sensors where you anticipate there will be, you can capture the load, the overloading problem. Go ahead.
I think that's about it for the questions. If there are any other questions, please free. Otherwise,
Hassan, you can open. Can they unmute and ask a question? That's fine too.
Yeah, we can. Absolutely.
Yeah, if somebody wants to ask question, talk. That's fine. Some people may not type it.
You guys, the participants, you can raise your hand, and we'll unmute you immediately, so that you can ask your questions. You don't need to write.
Yeah. We have time a little bit, so if somebody wants to ask question, and and I can speak Urdu too, okay? Or you want to speak Punjabi, that's fine too. Anybody has raised hand?
Sohail Kibriya Sahab, if you want to ask any question, I think you're on the road. Please don't. I hope you're not driving and listening, sir.
Thank you very much. I'm Sohail Kibriya, Dr. Haider, an ex-vice president of geotechnical engineering, and at the moment head of research and development in NESPAC. Right at the moment, I'm traveling on the motorway and listening to your comments about the loadings and the other measurements you see you were considering on the motorway, etc. A few questions, but my comments are that what would you think that what should be done to implement this system on the motorways at least? What at the level of NESPAC we should do? What is your recommendation?
I would strongly recommend, and I've talked to NHA last time I was there about, this was about more than a year ago. I think they should install these sensors in the main line for data collection, and one can monitor them. That can trigger you if there is more overloading, because then every vehicle has to pass that. You don't have to tell them, because if you have a weigh station, they can bypass that. But if you install sensor in the main line, some of those locations, and that can trigger if there is, what is the extent of overloading. Right now, I really don't know. I have done a lot of work in this area in Pakistan also. I still don't know what is the extent of overloading in Pakistan. And I have seen tremendous, one truck, probably 3 times the weight we were allowing at that time. But, it is really hard for me even to quantify what is the extent of that problem in Pakistan. So I think if you can convince people to install some sensors in the mainline pavement so that we can monitor 24 hours what's going on, that will give you some idea of what is the extent of overloading. And rather than, people all say, there's a lot of overloading. Sure, there is. But, it may be more than what we think. Or it may be not as clear as we think, right? So we need to quantify that first. That I think that is lacking. I didn't see a good data also from there. So I think if you can push, and I talked to member planning when I was there. So if you can push for in-pavement sensors, which is for data collection, I think that will be good. And they have weigh station. They understand the enforcement, but that enforcement will not give you the entire data. That's my question.
Thank you very much. We would further appreciate if it would be possible for you to share some of your publications on this particular topic, so that we may get more educated before we digest it and have discussion with the relevant quarters.
Yeah, sure. I can send a lot of publications. I will send it to Mark and he can distribute it. Right?
Thank you, Sohail sir. Thank you, Sohail sir, for the input. Ladies and gentlemen, although if there are still any questions, please raise your hand and we'll ask you, we'll get you online. Otherwise, we'll thank Dr. Haider because it's very late for him and it's way past midnight in
It's
Michigan.
okay. It's okay. I'm still awake. If somebody has question, we can have another 5 minutes. That's fine.
Okay, there is another question. Keeping
Go
in
ahead.
view the severity of overloading in Pakistan, these WIM technologies may not even work due to possible distresses.
Okay, that's a good question. Okay, so I talked about the site selection, right? So when you select a site for Vim sensor installation, it has to be a new pavement. You don't want to install a sensor which you are going to overlay or rehabilitate in 2 years, right? Because then you have to replace the sensor. So the site selection, it has to be on a straight portion of the road. We don't want to install it on the curves. So there are certain criteria. Your grade should be less than 2% because we don't want to install it on a higher grade. So there are certain criteria for selecting these sites. So if you select an appropriate site for, let's say, if we are installing quad piezo's, it can survive as long as your payment is good. The sensor will give you data. So it can survive its life. So that's not a problem. So you need to follow certain guidelines for the selection of site for that sensor.
Sir, I think we're not having any more questions. किसी ने उर्दू में सवाल करना है प्लीज उर्दू में कर लें कोई देयर इज नो ब्रेक लैंग्वेज नहीं है आप सवाल है it might be in any language but
नहीं,
the question
पंजाबी हासन पंजाबी में भी कर लो that's fine.
Bismillah ji, no issue.
I still remember. That's fine. Okay, so thank you very much, everyone, and thank you, Hassan.
Thank you, sir. Thank you for your time,
thanks.
It was a pleasure having you here.
I will send some of my publications. I will send you the PDFs, and then you can share with people, right?
I'll ask Umar Saab for the last closing comments. Umar Saab, you're on. Please unmute. Yeah, all right.
Ji, Waqar, thank you very much. You did a great job with great information. और हमारे सारे जो हाईवेज के और मैं देख रहा था बहुत सारे लोग हैं हर तरफ से इस्लामाबाद पेशावर से भी और कराची में भी हैं ये लोग so people have actually benefited from your research और आपकी जो it's very gracious of you to allow to give us some आपकी information about your own research work आप मुझे we can always go forward on that और हमारे if you want somehow हमारे नेस्पा के लोग हैं और वो कोई रिसर्च पेपर में आप लोगों की हेल्प कर सकें आपकी as a student तो आप हमें बताएं कि we'll highways वाले are there they've done a lot of work also so we'd appreciate that NHA के साथ तो आप कर ही रहे होते हैं मगर नेस्पा के कुछ बच्चे ऐसे हैं जो कि those who are doing their PhDs and masters in transportation civil engineering यहाँ पे so we greatly appreciate your help also once again thank you Waqar past your and thank you very much you've always been there
I started my career by joining NESPAC back in 89-90. So that was my first, so it's a pleasure actually. What I have probably given you some information people don't know. In fact, I wanted to talk about this because we have less exposure there. But in general, people understand why we do this. So I think there is a need there for these type of technologies and then with some understanding, we can improve overall pavement performance in Pakistan. But this is one of the important data we need to have, other than quality control, pavement design, and all other factors in pavement. Okay.
Thank you, sir. Thank you again.
Okay.
Ladies and gentlemen, thank you for joining us again for an awesome session. We are going to have next week Shujaudeen
Sheikh Shujauddin.
Sheikh Shujaudeen, sorry, for a session, and that's more of a religious and Islamic point of view. So we'll see you next Thursday. Take care. Allah Hafiz. Thank you, sir.
Okay.
Thank you, Mr.
Bye, sir. Khuda
Bye-bye.
Hafiz.
Allah Hafiz.